Hello everyone. In a previous class, we will discussed about what is DC machine, its classification, its armature windings and the EMF equations of the DC machine. So this is the third lecture for the unit number 1. Lecture we will study about what is armature reaction in a DC machine and its effect, method for limiting armature reaction, commutation process means what is it and how to limiting or minimize the commutation process. Next we will move on method for limiting commutation and then reference. So this is the outline of this presentation. Inside this we will study about what is the armature reaction and the commutation process and how to minimize these two things. So let's start with the armature reaction introduction. In a DC generator, the purpose of field winding is to produce magnetic field called a main flux, whereas the purpose of the armature winding is to carry armature current. Although the armature winding is not provided for the purpose of producing a magnetic field, nevertheless, the current in the armature winding will also produce magnetic flux called as armature flux. The armature flux distort and weakness the main field or main flux, posing problem for the proper operation of the DC generator. The action of the armature flux on the main flux is called the armature reaction. Actually in a DC machine, जो DC machine है हमारी उसमें दो तरीके के flux generate होते हैं because the DC machine consists two main winding. One is called the field winding placed on the stator and that is called the armature winding placed on the rotor. तो हमारी ये जो दो वाइंडिंग है दोनों ही वाइंडिंग मैग्नेटिक फ्लक्स को प्रोड्यूस करती हैं. तो इन दोनों फ्लक्स का जो इंटरेक्शन है या इफेक्ट है आर्मेचर फ्लक्स का फील्ड फ्लक्स पे और फील्ड फ्लक्स के आर्मेचर फ्लक्स पे जो इफेक्ट है इस इफेक्ट से ही आर्मेचर रिएक्शन होती है और इसी इफेक्ट को हम आर्मेचर रिएक्शन बोलते हैं. नेक्स्ट, in a DC machine, the carbon brushes are always placed at the magnetic neutral axis like M and E. In no-load condition, the magnetic neutral axis coincide with the geometrical neutral axis like G and A. Now, when the machine is loaded, the armature flux is directed along the interpolar axis, the axis in between the magnetic poles, and is triangular in wave shape. The result an armature current flux directed along the brush axis and the cause cross magnetization of the main field. This cross magnetizing effect result in the concentration of the flux at the trailing pole tip in the generator action and at the leading pole tip in the motor action. So this is a main definition or main slide. What is armature reaction? So the effect of magnetic field set up by the armature current on the distribution of flux under the main pole of a generator. The armature magnetic field has two effects. It's demagnetize or weakens the main flux, and second, it's cross magnetized or distort it. So this is a diagram. In this diagram, You can see both the axes like MNA and GNA. So the main definition in short, what is armature reaction? The armature reaction is the effect of the armature flux on the main flux. तो आर्मेचर रिएक्शन को हम एक लाइन में सीधा डिफाइन कर सकते हैं कि जो आर्मेचर रिएक्शन होती है वो इफेक्ट होता है आर्मेचर फ्लक्स का मेन फ्लक्स पे. So this is the main definition. The armature reaction is the effect of the armature flux on the main flux is called as armature reaction. In case of DC motor, the resultant flux is stranded at the leading poles and the weakened at the trailing poles tip. Let us discuss these effects of armature reaction considering a two-pole generator. Actually, in an armature reaction, there is a three effect. Number one, magnetizing. Number two, demagnetizing. And number three, cross-magnetizing effect. In a magnetizing effect, the armature flux and field flux in a same direction. So, the core is magnetized. In a demagnetizing effect, the armature flux and main field flux is opposed to each other. So, they cancel out their effect and the core is demagnetized. So, this is called the demagnetizing effect. Third one is called the cross-magnetizing effect. So, in this effect, the field flux is perpendicular to the armature flux. So, this effect is known as the cross-magnetizing effect. So, let us discuss these effects of armature reaction by considering a two-pole generator. So, this is a diagram. In this figure, show the flux due to the main flux when the armature conductor carry no current and the flux across the air gap is uniform. The MMF producing the main flux is represented in magnitude and the direction by the vector OFM. You can see the diagram OFM in a figure 1. Note that OFM is perpendicular to GNA. Now in figure number 2, show the flux due to current flowing in armature conductor alone, means main pole unexcited. The armature conductor to the left of GNA carry current in X direction and those to right carry the current outside or dot. The direction of magnetic line of force can be found by the corkscrew rule. It is clear that the armature flux is directed downward parallel to the brush axis. So the MMF producing the armature flux is represented in magnitude and the direction by the OFA, vector OFA. You can see the diagram in figure 2. The figure 3 show the flux due to the main pole and that due to current in the armature conductor acting together. The resultant MMF OF is the vector sum of OFM and OFA as shown in figure 3. Since MNA is always perpendicular to the resultant MMF, the MNA is shifted through an angle Q. Note that MNA is shifted in the direction of the rotation of the generator. You can see the diagram. Next diagram, in order to achieve sparkless commutation, the brush must lie along the MNA. Consequently, the brush are shifted through an angle Q so as to lie along the new MNA as shown in figure number 4. Due to brush shift, the MNA FA of the armature is also rotated through the same angle of Q. It is because some of the conductors which were earlier under N pole now come under S pole and vice versa. The result is that armature MMF FA will no longer be vertical downward but will be rotate in the direction of the rotation through an angle Q as shown in a figure number 4. Now FA can be resolved into rectangular component FC and FD. So the component FD is the direct opposition to the MMF OFM due to the main pole. It has a demagnetizing effect on the flux due to main pole. For this reason, it is called the demagnetizing or weakening component of the armature reaction. And the component FC is at right angle of the MMF OFM due to the main poles. It distorts the main field. For this reason, it is called the cross-magnetizing or distorting component of the armature reactions. It means FD जो है वो हमारा weakening component of the armature reaction कहलाएगा और FC जो हमारा कहलाएगा वो distorting component of the armature reaction. So it may noted that with increasing of armature current, both demagnetizing and distorting effect will be increased. Now the conclusion is that number 1, with brush located along GNA, that is Q is equal to 0 degree, there is no demagnetizing components of the armature reactions, means FD is equal to 0. There is only distorting or cross-magnetizing effect of the armature reaction. Point number 2, with the brushes shifted from GNA, armature reaction will have both the demagnetizing and distorting effects. Their relative magnitude depend on the amount of shift. The shift is directly proportional to the armature current. Next point, the demagnetizing component of the armature reaction weakens the main flux. On the other hand, the distorting component of the armature reaction destroys the main flux. Point number next 4th, the demagnetizing effect lead to reduced generated voltage while the cross-magnetizing effect lead to sparking at the brushes. Now the demagnetizing and cross-magnetizing conductor or effect. With the brushes in the GNA position, there is only cross-magnetizing effect of the armature reaction. However, when the brush are shifted from the GNA position, the armature reaction will have both the demagnetizing and cross-magnetizing effect. Consider a two-pole generator with brush shifted or lead. QM is a mechanical degree from GNA. We shall identify the armature conductors that produce demagnetizing effect and those that produce the cross-magnetizing effect. Number 1, the armature conductor OQM on either side of the GNA produce flux in the direct opposition to the main flux as shown in figure 1. Thus, the conductor lying with an angle AOC is equal to BOD is equal to 2QM. At the top and the bottom of the armature produce demagnetizing effect. These are called demagnetizing armature conductor and constitute the demagnetizing ampere turn of the armature reaction. So this is a diagram number 1 and diagram number 2. So number 2, the axis of magnetizing of the remaining armature conductors lying between angle AOD and COB is at right angle to the main flux as shown in figure 2. These conductors produce the cross-magnetizing or distorting effect. That is, they produce uneven flux distribution on each poles. Therefore, they are called cross-magnetizing conductors and constitute the cross-magnetizing ampere turn of the armature reaction. So, these two diagrams show the cross-magnetizing as well as the demagnetizing conductor ampere turn and its effect. Now we will move the next topic, the method for limiting the armature reaction. Before moving this, we can summarize what is armature reaction in a short. Armature reaction is a effect of main field armature flux, effect of armature flux to the main field flux. मीन्स आर्मेचर फ्लक्स का मेन फील्ड फ्लक्स पे जो इफेक्ट होता है उसको हम आर्मेचर रिएक्शन बोलते हैं। आर्मेचर रिएक्शन के बेसिकली 3 इफेक्ट होते हैं जिसको हम बोलते हैं मैग्नेटाइजिंग इफेक्ट, डीमैग्नेटाइजिंग इफेक्ट और क्रॉस मैग्नेटाइजिंग इफेक्ट। तो अब हम देखेंगे कि इनको लिमिटिंग कैसे कर सकते हैं। सो मेथड फॉर लिमिटिंग द आर्मेचर रिएक्शन। There are 3 methods to limiting armature reaction. Number 1, by using compensating bindings, using interpoles, and by using the brush shift, we can limiting the armature reaction. So number 1, compensating binding. The cross-magnetizing effect of the armature reaction may cause trouble in a DC machine subjected to large fluctuation in load. In order to neutralize the cross-magnetizing effect of the armature reaction, a compensating binding is used. So this is the diagram for the compensating binding. A compensated binding is an auxiliary winding embedded in a slot in the pole face as shown in a figure. It is connected in series with the armature in a manner so that the direction of current through the compensating conductor in any one pole face will be opposite to the direction of the current through the adjacent armature conductors. So this is a proper way or proper diagram for the compensated winding. Now next is a brush shift. So a neutral solution or a natural solution to the problem appear to shift the brush along the direction of the rotation in a generator action and against the direction of the rotation in motor action. This would result in a reduction in air gap flux. This will reduce the induced voltage in a generator and would increase the speed in motor. Brush shift has serious limitation, so the brushes have to be shifted to a new position every time the load change or the direction of the rotation change or the mode of the operation is change. Limited only to very small machine means this techniques, brush shift techniques, is applicable only for a very small rating machine. Here also the brushes are fixed at a position corresponding to its normal load and the mode of operation. Due to these limitations, this method is generally not preferred. Means it is not preferable method. Next is a interpole. By using interpole, so the limitation of the brush shift has led to the use of interpole in almost all the medium and large size of DC machine. Interpole are long but narrow pole placed in the interpolar axis. They have the polarity of succeeding poles, means coming next in the sequence of rotation in a generator action and producing which has passed behind in the rotational sequence poles in the motor action. The interpole is designed to neutralize the armature reaction MMF in the interpolar axis. Since interpolar or interpoles are connected in series with the armature, the change in the direction of the current in the armature change the direction of interpoles. This is because the direction of armature reaction MMFs is the interpolar axis. It also provides commutation voltage for the coil undergoing commutation such that the commutation voltage completely neutralizes the reactance voltage, like L di by dt. Thus, no sparking takes place. So, in this diagram, you can see the interpole, main field pole, and other components of the DC machine. Interpolar windings are always kept in series with armature, so interpolar winding carry the armature current. Some important note: the cross-magnetizing armature reaction effect is mainly caused by the armature conductor, which are located under the pole arc. At the high load, this effect of the armature reaction may cause excessive flux density in the trailing pole tip in a generator and the leading pole tip in a motor. Due to saturation in the pole shoe, the increase in a flux density may be less than the reduction in the flux density in remaining section of the pole shoe. This would ultimately result into a net reduction in a flux per pole. This phenomena is thus known as demagnetizing effect of the cross-magnetizing armature reaction, which is further compensated by the use of the compensating winding. The next note is interpolar windings and compensating windings are connected in series with the armature winding, but on the opposite side with respect to the armature. The primary duty of the interpolar winding is to improve the commutation process, and that of the compensating winding is to compensate for the increase or decrease the net air gap flux, that is, to maintain its constant value. Now we will move the next topic, commutation. So what is it? So the reversal of the current in a coil as the coil passes the brush axis is called the commutation. It's a single line definition of the commutation. I repeat again. The reversal of the current in a coil as the coil passes the brush axis is called as commutation. So the current in the coil connected to a brushes are either all towards the brushes, mean positive brush, or all directed away from the brush, means negative brush. Therefore, current in a coil will be reversed as the coil passes a brush. This reversal of the current as the coil passes and brush is called commutation. In a diagram, so consider the two-pole lap-bound generator or this schematic diagram of two-pole lap-bound generator. There are two parallel paths between the brushes. Therefore, each coil of the winding carry one half of the total current IA. IA means armature current entering or leaving the armature. When commutation takes place, the coil undergoing commutation is short-circuited by a brush. The brief period during the coil remains short-circuited is known as the commutation period, represented by DC. If the current reversal is completely by the end of the commutation period, it is called the ideal commutation. If the current reversal is not completed by the time or by that time, then the sparking occurs between the brush and the commutator, which result in a progressive damage to both. The next we will study about how to improving the commutation or method for improving the commutation. So To make the commutation satisfactory, we have to make sure that the current flowing through the coil completely reversed during the commutation period attained its full value. There are three main methods for improving the commutation. These are number 1, resistance commutation, number 2, EMF commutation, and number 3, compensating binding, or by using the compensating binding. So the first is a resistance commutation. In this method of the commutation, we use the high electrical resistance brushes for getting spark less commutation. This can be obtained by replacing low resistance copper brushes with the high resistance carbon brushes. We can clearly see from this picture that the current IC from the coil C may reach to the brush in two ways in the commutation periods. One path is direct through the commutator segment B and to the brush, and the second path is the first through the short circuit coil B and then through the commutator segment A and to the brush. When the brush resistance is low, then the current IC from the coil C will flow the short circuit path. That is, the first path, as its electrical resistance is comparatively low because it is shorter than the second path. So when a high resistance brush are used, then as the brush moves towards the commutator segments, the contact area of the brush and the segment B decrease, and contact area of the segment A is increased. Now as the electrical resistance is inversely proportional to the contact area, then resistance RB will increase and resistance RA will decrease as the brush moves. Then the current will prefer the second path of the reach to the brush. Thus, by this method of improving commutation, the quick reversal of the current will occur in the desired direction. We know that the resistance R is equal to rho L by A, where R is called the resistance, rho is called the resistivity of the material, L is called the length of the conductor, and A is called the cross-sectional area of the conductor. A is the cross-sectional area of the conductor. Here is this description. It is used as a contact area. You can see the diagram, RA and RB, and the current IC. Now we will move to the second method, EMF commutation. The main reason of the delay of the current reversing time in the short circuit coil during commutation period is the inductive property of the coil. In this type of the commutation, the reactance voltage produced by the coil due to its inductive property is neutralized by producing a reversing EMF in the short circuit coil during commutation period. Reactance voltage. The voltage rise in the short circuit coil due to inductive property of the coil, which oppose the current reversal in it during the commutation period, is called the reactance voltage. We can produce reversing EMF in two ways. Number 1, by brush shifting, and number 2, by using interpole or commutating poles. Brush shifting method of commutation. In this method of improving commutation, the brushes are shifted forward direction for the DC generator and in the backward direction for the motor, for producing a sufficient reversing EMF for eliminating the reactance voltage. When the brush are given the forward or backward lead, then it's bring the short circuit coil under the influence of the next pole which is of the opposite polarity. Then the side of the coil will cut the necessary flux from the main pole of the opposite polarity for producing the sufficient reversing EMF. So this is a diagram for generator rush shift. This method is rarely used because for best result, with every variations of load, the brush have to be shifted. So this method is rarely used, not used frequently. Method of using interpole. So this is the interpole diagram for interpole commutation. You can see the main pole as well as the interpole. In this method of the commutation, some small poles are fixed to the yoke and placed between the main poles. These poles are called interpoles. Their polarity is same as the main pole situated next to it for the generator, and for the motor the polarity is same as the main pole situated before it. The interpole include an EMF in the short circuit coil during the commutation period, which oppose reactance voltage and give sparkless commutation. Next is a compensating winding. This is the most effective mean of eliminating the problem of armature reaction and the flashover by balancing the armature MMF. Compensating windings are placed into the slot provided in the pole face parallel to the rotor or armature conductors. The major drawback with the compensating winding is that they are very costly. Their use is mainly for the large machines subject to heavy overloads or plugging, and in a small motor subject to sudden reversal and the high acceleration. So now we will move the references. So this is the reference. We use the books Electrical Technology by V.L. Theresa and some sites like Electrical for You. And thank you everybody for watching this video.